Hello everyone, this is the challenge question walkthrough for Edexcel's Applied Year 2 textbook, Chapter 3 on statistics. Okay, so our first question is from exercise 3E. We've got a normal distribution with mean mu and variance sigma squared, and it has interquartile range Q. And then part A asks us to show that sigma is equal to 0.742Q, where the coefficient of Q is correct to 3 sig fig. So, because here we don't have specific values for mu and sigma, we need to use the standardized normal distribution. So we need to go from x having mean mu and variance sigma squared to the z distribution with the mean of 0 and standard deviation 1. And to do that, we need to use the formula z is equal to x, take away the mu to center at 0, and then dividing by the standard deviation. Okay. So we need to find the interquartile range. So we need to find the values for which the probability of x being greater than the upper quartile, Q3, is 0.25, and the probability that x is less than the lower quartile, Q1, is equal to 0.25 also. And to do that, we need to use the standardized normal distribution. So let's first find the z values for which this is true. So here we've got the mean of 0 for the z distribution. And we need to find this value here and this value here, for which this area here is 0.25, and this area here is 0.25. And to find out the z values, you can use your calculator. So on the class whiz, it's in 7 for distributions, then 3 for inverse normal. So this one here is going to be where the area to the left is 0.25, and the standard deviation is 1, and the mean is 0. That gives us minus 0.67448, so on. And then this value here, by symmetry, is then going to be positive 0.67448. Okay, so those are our two z values. That means our x values, the actual values on the distribution that we're looking for. If I draw that down here in black, so it has mean mu, and then we're looking for these values here then, where the probabilities here are 0.25 here and here. Then we need to use this formula to find these x values. If we rearrange, then we get that x is equal to mu plus sigma z. So these two x values here are then going to be mu plus or minus 0.67448 sigma. Therefore, our interquartile range is going to be the difference between these two values. So the interquartile range is equal to Q is equal to mu plus 0.67448 sigma, take away mu minus 0.67448 sigma. So that then gives us two lots of 0.67448 sigma. Then if we rearrange for sigma here, we're going to have dividing both sides by 2 times 0.67448. Sigma is equal to 0.7413 Q, and to 3 sig fig, that is 0.741. And the textbook is actually wrong here. It should be 0.741. I've checked with the solution bank and they agree with me. So there we are. Sigma is equal to 0.741Q. Now for part B, explaining why it's not possible to write mu in terms of Q only. Well, the interquartile range is actually independent of the mean, as is shown here. When we find the interquartile range, we're just, we cancel out the mu's essentially. So the interquartile range, Q, is independent of the mean. And if you think about what this means intuitively, so Q is independent of mu. Well, mu is the mean, it's the measure of central tendency. Whereas Q is a measure of spread. So yeah, the mean mu could be 40, could be 40,000, could be 0.1, doesn't matter, because Q is completely independent um, of this mean. You could think about it as moving this distribution along. Like we could move it to the right and it'd be here, and the interquartile range would still be the same with a different mean mu. It could be here, and the same story. Um, so yeah, the interquartile range is completely independent of the mean. And moving on to our final question from mixed exercise 3. A football manager claims to have the support of 48% of all the club's fans. A random sample of 15 fans is taken, and part A asks us to find the probability that more than 8 of these fans supported the manager. So, we here are going to assume that the manager's claim is correct. So, we've got then a binomial distribution with 15 trials, the 15 fans, and the probability of success 0.48. Okay, and now we want to find the probability. Should have written really here, x is modeled by that distribution. Then we can find the probability that x is greater than 8, the probability that more than 8 of the fans supported the manager. That is equal to 1, take away the probability that x is less than or equal to 8. And putting that into your calculator will give you 1 take away 0.74903, which is 0.251024 sig fig. Okay, for part B then, a second random sample of 250 fans was taken and is used to test the football manager's claim at the 5% significance level. Use a suitable approximation to find the critical regions for the test. Okay, so here we need to use an approximation as the question hints towards. So the binomial, the true distribution, is going to be 250, and then assuming the manager's claim again, the probability of success is 0.48. And then the approximation, because n is large and p is almost equal to 0.5, that means we can take a normal distribution with mean np, which is 250 times 0.48. And you put that into your calculator, will give you 120. And then the variance is going to be np1 minus p. So that's going to be the 120 times 0.52. And putting that into your calculator gives you 62.4. So our mean is 120 and the variance is 62.4. I'm just going to remember to square root that when we find probabilities with our calculator. Okay. Now for these critical regions, we need to find these values C, or C1 and C2. So the first one is where y is greater than this critical value. This first critical value is going to be equal to 0.05. Or actually, if we're doing this as a two-tailed test, we need to be 0.025 because we're halving the significance. So that for the top tail, and then for the bottom tail, we're going to have the probability of y being less than the second critical value is also 0.025. Okay, so let's find these in. Let's go to the inverse normal distribution, and let's go first for this bottom one here. So if we think about what this looks like on a little diagram. Okay, so this is the mean 120. This value is going to be somewhere here, somewhere down there. So that's C2, that's C1. And we need this probability here to be equal to 0.025, and this probability here also to be equal to 0.025. I haven't drawn that really well here, but it's meant to be symmetrical. Okay, so inverse normal on your calculator, 0.025 for the area. Sigma, this is going to be the square root of 62.4, and then the mean is going to be 120. So that gives us a critical value of 104.517 for C2. And then for C1, that's going to be the area is then going to be this whole area over here. So it's 1 take away 0.025, which is 0.975. So the second critical value is then going to be 135.482. Now if we think about the continuity corrections before we write our critical regions, then here's the normal distribution we've got. Then we're going to look at these two bars here, representing 104 and 105 on the binomial distribution. When we approximate them with the normal distribution, then we apply the continuity correction. So 104.517 lies just beyond this point here for the 105 bar, because 105 includes 104.5 up until 105.5. So actually the critical region here is going to be y is less than or equal to 105. That is included because of the continuity correction. And then if we do a similar sort of thing with where we've got on the other side this 135 and 136. So this is 135, this is 136. Then the 135.482 is going to be contained in this bar here, because the 135 goes between 134.5 up until 135.5. So the other part of the critical region then is going to be y is greater than or equal to 135. And then for part C, we just need to conclude and comment on the manager's claim. Well, 102 is in the critical region. So there is sufficient evidence at the 5% level to reject the manager's claim. And that is the end of this challenge question walkthrough for Edexcel's Applied Year 2 Chapter 3. I hope you enjoyed this video and found it useful, and I'll see you next time.